All right, on to the second half of this. We are finding the equation of a tangent line, standard calculus stuff at this point 1, 2. I hope 1, 2 works out. 1 squared is 1, 2 times 1 times 2 is 4, that's 5, minus 4 plus 1 is indeed 2. Okay, that checks out. That's always reassuring. All right, so to find the tangent line, we need to take the derivative. What is y prime? If we could find an explicit function, we could do that. Y prime is what we're after. So this becomes 2x plus, and then we've seen this before, it's 2 times the derivative of this, which is going to be, it's xy prime plus y, and then minus 2y y prime. Again, it's implicit differentiation. We've got to deal with the y prime there. Plus 1 then equals 0. All right? Well, we know what x and y are. We're only after y prime. So this is a really smart time, I think, to substitute in those values. So that's 2 times 1 plus 2 times, and that's y prime. That's just 1 times y prime is y prime, plus 2 minus 2 times 2, and then that's y prime, plus 1 equals 0. Okay? So I'm just subbing in the things I know, x and y, and I'm going to work out what y prime is. So let's see, that's 2 plus 2y prime plus 4 minus 4y prime plus 1 equals 0. Gather up my like terms. That's a negative. I'm going to move that over. That's 2y prime, right? Saving some steps. Negative 2y, move it over. 2 plus 4 is 6 plus 7. And so y prime then equals 7 halves. Okay? Well, I've got a point and I've got a slope, so I'm basically done. It doesn't say in what form, so point slope form works. Y minus 2 equals 7 halves x minus 1. You can convert that into y equals mx plus b if you have a particular obsession with that. Go for it. Moving right along, however, linear approximation. Okay, this is that whole concept that this, we're going to model this with the function f of x is equal to x to the 7th, and then rely upon the fact that we are good at multiplying 10 by itself a whole bunch of times. So we know that f of 10 is equal to a 1 with 7 zeros. So what is that? 10 million. All right. So we have to sort of imagine that we've got this x to the 7th, and it's zooming up like this, super steep, way out here at 10. It's going to be a super steep slope, and we're going to use that idea of local linearity to make the prediction about a little bit more than 10, and then come up with an approximation based on that. So all I need to do is find the derivative of x, of the function with respect to x, which is 7x to the 6th. And then what is that point that we're dealing with here? What is the slope at that point? And when I plug in 10, that's going to be 7 times 10 to the 6th. Well, that is 7 million, right? Right. 7 and 6 zeros. Okay, so this point out here is 10 comma 10 to the 7th, just to simplify writing. A whole bunch of zeros gets boring after a while. All right, so now I've got a point and I've got a slope, so a lot like this problem up there. I can write it that way if I want to. It's almost easier to think about what is the change going to be based on that, and that would be more of the differential approach. But just doing it this way, grinding it out, it's going to be y minus, and this is, again, I'm using the point I'm given and the slope I found, point slope form, 10 to the 7th equals 7, I guess instead of 10 to the 6th, I'll write this one out, times x minus 10. Okay, point slope form. Well, I know that my new x value is going to be 10.123. So when I take away 10 from that, y minus, well, let's just go right to the chase. Y is going to be equal to, when I move this over, and I plug in here the value I'm going to estimate, 10.123, subtract 10 from it, It's going to be 7 million times 0.123 and then plus my 10 million, all right? So when I multiply this by 7 plus 140 plus 21 is 861. Move 6 decimal places. Y then is equal to 861,000 plus and then 10 million, which is going to give me a final answer of 10,861,000, and that's it. Checking a calc. I suspect this is going to be too low because it's curving ever upwards, so it's going to be somewhat larger than that. You can check and see how much larger. All right, on to this. The graph of this position function of a particle shown below, where it represents t is time in seconds. Okay, so this is the position function, like s of t, like we've done before. Here's our sort of graph problem. Get your slopometers out. This is some negative slope. I'm going to give it an arbitrary value, I don't know, right there. Critical thing is here's where it's 0. So it's maybe going upwards like this, and then looks like right here it's at its steepest, and here it's 0 again. So whatever it does, it's going to go up and then come down. So that looks pretty sensible, kind of a nice curve. And then it's going to go sort of ever steepwards downwards after that. So that is my velocity then, my change in the position with zeros here and here. And then my acceleration, this is some positive value that's getting less and less and less positive till right there where it's 0. So that positive value then, I'm going to give it a dotted line coming down, aiming for that spot right there, and then going, looks like, ever downward. All right? Well, the critical thing is that wherever there's a 0 of our first or our second derivative, draw a little boundary. And here's a 0 for the second derivative. Draw a little vertical boundary. And here's a 0 for our first derivative. And then just ask yourself, the simple question is, what's the derivative doing? Here it is negative, and up here the second derivative is positive. Here they are both positive. There's a positive and there's a positive. So this is where it's speeding up, right in here. And here it's positive and negative, and here it's negative and negative. So here on out is also where it's speeding up. So when is the particle speeding up? It is speeding up if this is 1, 2, 3, 4, and 5. It's when x is greater than 2 and less than 3, 2 to 3, and when it's 4 and greater, when x is greater than 4. That's the speeding up part. Okay? When is it slowing down? I'm just going to use interval notation to save time. 0 to 2, and then from 3 to 4 is when it's slowing down. Okay? The explanation, I just gave it verbally. You guys can jot down a few key points. If you remember, we had the rule, I forget who gets credit for that, Dan or somebody, and we were saying that if it's concave, if the function, the original function is concave down and decreasing, it'll be speeding up, in this case, in the negative direction. And if it's concave up and increasing, it'll be speeding up, in this case, in the positive direction. So if you find that as a way of checking or working faster, you can do that, but I might ask you to sketch the derivatives and talk about it in more detail, because I think that's the important point for you guys to understand. All right, last problem. The table gives this population. I have saved some time here by putting it into my calculator, and let's hope it's still there. It's not crashing. No pinwheel of death in this baby. So let's see. If I go to Stat and Edit, I have put in the year only the last 2 digits. I think that is a big saver. Adding on big numbers just makes your resulting functions awkward and lots of zeros or something. Here are the values. I went zoom 9, and there it is. Okay. Then I went to Stat and over to Calc, and I did cubic reg, so 6. I don't know if you know this little trick here, but if you go down to store the equation, I'm going to hit the vars key, okay? And with the vars key, I go over to y variables, I choose function, I'm going to patch it down here to number 3, and I hit enter, and it's going to stick it in y3, you'll see why. And I just go there and hit enter, and it's thinking, and there it is. And if I go to my y equals, here it is down here, okay? Now there is a whole lot of digits, all right? So what I have done is I have just chopped it, and you can see from 00128, you're only losing a couple of percent error. And I have greatly simplified this top one. This equal sign is dark, so if I hit graph, there is the regression function, which is pretty good, okay? And then if I go to y equals, and if I turn this equal sign on, now they're both on, I hit graph, and you'll see that even though I've radically simplified the digits, there's almost no perceptible change between the functions, okay? So on the test, if you're asked to work with the results, you can round to the nearest like 2 significant digits, and you should be fine, okay? You got that, 2 significant figures. You should know that from what that means from your science class. Except maybe I could have made that, well, 16 or 1700 probably even would have been fine, okay? But that's skipping ahead a little bit. I want to get that in here. Estimate the population growth, the rate, that is by using 2 secant lines, okay? So if it's 120, there's been a change in the x's of 10, all right? And the change right here is 210, okay? So I'll put that there. 210 divided by 10 gives me a rate of change that's equal to 21, that's people per year, okay? If I do it going in this direction, secant line here, I will get from 725 to 835, that's 110 per 10 years, so that's 11, okay, people per year. So if I then average these, 32, that's 16, I'm getting 16 people, can't spell right quickly at the same time, per year. All right. Use a graphing calculator to find the cubic function. I've done that. I have simplified it here, and I've got y equals, and I made it 0.0039x squared. Whoops, 13. I'm getting ahead of myself. 0013 x to the third, and then plus 0.31 x squared, and plus 0.37x, and plus 1663, okay? So to find a model for the rate of population growth, this is calculus teacher code for find the derivative, all right? And when I find the derivative, I bring the 3 out front, and now I get my 0.0039x squared plus, and then that's 0.62x plus 0.37, okay? And then I'm going to use this to plug in 1920. In the interest of time, I'm not doing 1980. I want to keep this under a 3-hour video. And when I plug in 20, because I've taken out the 19, and I work that out, it's going to be 400 times that, and 20 times that, plus 37. And I believe when I did it before, you get an answer of around 14, okay? So you can check on your own, do your own work, and you'll see that 14 is pretty close to 16 when it comes to this sort of estimation of the slope of a curve, okay? So sketch that in and make it look all pretty, and you'll be good. Good luck. Bye-bye.